Welcome to this video in our HVAC design series. Now that you understand what thermal loads are and where they come from, let's take it a step further. How do architectural design choices affect those loads? We'll look at how mass, sunlight, and orientation all shape the way heat moves through a building over time, and why timing is just as important as quantity. Here's what we'll explore in this video. First, we'll see how building orientation changes solar gains. Then we'll talk about thermal mass and how it affects load timing. We'll look at some design comparisons to reinforce the concepts. And finally, we'll practice explaining this behavior to others, a key skill for collaboration. In this video, you'll strengthen your ability to anticipate how buildings behave thermally, even before the calculations begin. You'll also practice explaining why thermal load dynamics matter for HVAC sizing and design coordination. This is about thinking like a designer and communicating like an engineer. Let's say you're designing HVAC systems for two identical buildings in the South Hemisphere. One faces south, the other west. Which one will need more cooling in the afternoon? And what design choices could you reduce that load? This is exactly what we'll unpack in this video. Design decisions such as orientation and glazing directly impact how much heat enters a building. South-facing windows get consistent solar gain during the day, while west-facing windows experience intense afternoon sun. The size, type, and placement of windows, along with shading devices, determine how much solar energy becomes a load. We use solar heat gain coefficients, or SHGC, to describe how much solar radiation is transmitted through a window. A lower SHGC value means less solar gain. These decisions affect both peak cooling loads and energy efficiency. Thermal mass, the ability to absorb and store heat, can help shape thermal loads in time. A concrete floor, for example, can absorb solar energy during the day and release it gradually later. This delays the moment when the HVAC system must respond. In HVAC terms, this means that thermal mass reduces the rate at which indoor temperature rises, effectively flattening and delaying the peak load. This principle is especially useful for load shifting strategies and energy efficiency design. Beyond HVAC, thermal mass is a foundational element of passive architecture. It helps maintaining indoor comfort with minimal mechanical input by buffering temperature swings. In climates with a large day-night temperature difference, buildings with a high thermal mass can absorb heat during the day and radiate it inward at night, reducing or eliminating the need for heating and cooling. Properly placed mass, like exposed walls or floors in sunlit zones, plays a central role in passive solar strategies. Let's compare a few design strategies and how they influence thermal loads behavior. Lightweight constructions respond quickly to outdoor conditions and solar gains, which can result in sharp and early thermal peaks, especially when paired with large unshaded windows facing the west. In contrast, heavy constructions equipped with thermal mass can delay these fluctuations, reducing peak load demands. When glazing ratios are high and unshaded, especially on solar exposed facades, solar gains significantly increase. Conversely, low glazing ratios or well-shaded windows reduce these gains, improving comfort and lowering cooling loads. By comparing these features, mass, glazing, orientation, and shading, we can understand how design influences both the timing and magnitude of thermal loads. These insights support better HVAC sizing and more effective passive design strategies. Finally, understanding is not enough. we must be able to communicate. Dynamic thermal load behavior refers to how heat gains become HVAC demands over time, not instantly. This delayed or time lag is critical for peak load calculations and indoor comfort. Architects, clients, and stakeholders often need help visualizing these effects. For instance, explaining how insulation and mass affects a building heats up or cools down, or how solar gains from west-facing glass lead to late afternoon cooling loads, makes technical choices more reliable. Communicating this clearly with diagrams builds trust, strengthens design collaboration, and ensures HVAC systems are properly sized and controlled. It's not just technical insight, it's essential design communication. To sum it up, design doesn't change how much heat enters a space, it changes when that heat becomes a load. Good orientation, smart sizing, thermal mass, and passive techniques help us smooth out peaks and improve comfort. Understanding and communicating these patterns is at the heart of effective HVAC design. This video shows you how to connect architectural design to HVAC performance. In the next lessons, we'll dig deeper into load estimation techniques and control strategies. You will see how real design decisions play out in calculations, and how to create systems that are both efficient and comfortable. Keep going, you are building real expertise.